talk about something that is different. So you guys heard a lot about 5G and the Internet of Things, millimeter waves, centimeter waves, new radios, all of that stuff. But I'm just gonna say I agree with all of that, so there is no point repeating it. So this is why I decided to choose something that even let us stretch our imagination more and think about other usage cases of wireless altogether. And that's part of the Internet of Things, part of how I think the environments are going to change and our interaction with both the network and computing devices is going to change in the future. So I'm going to talk about smart environments that can monitor your breathing and heart rate with wireless signals remotely without touching your body. So increasingly, we see smart homes that have all sorts of sensors, temperature sensors, air control sensors, other types of sensors that monitor everything and adapt the environment to the well-being and the comfort of the people. So why not to ask, why not having smart homes also monitor our vital signs? Right? If they can monitor our breathing and heart rate, then you can start seeing so many interesting applications. For example, I can start asking my smart home, like, do my breathing and heart rate reflect a healthy lifestyle? Or, is my baby breathing normally when she sleeps? How is her breathing? Then stop worrying about it. And my elderly parent, I can check that she's all the time having a regular heartbeat. There are no problem with breathing or heartbeats. And not only this, I mean, there's so much, actually, a significant percentage of the population that has sleep apnea that is not even diagnosed because they don't even think about going to a sleep lab. So you can remove all of that stuff that you have to put on you to test sleep apnea, and your home can test your sleep apnea for the whole life and tell you at any time when there is any risk. And beyond that, once you start understanding breathing and heart rate and have ubiquitous ways of measuring them, then you can imagine the environment choosing it. In fact, there are multiple studies where you use heart rate and variability in heart rate to discover use and stress level, and then you can adapt the environment, probably adapting the lighting, adapting the music to suit our needs. So, but how can smartphones measure our breathing and heart rate? I mean, of course there are wearables. But wearables can be really cumbersome. Like imagine having to wear all the time a nasal probe on your nose so that you can measure breathing. You really wouldn't do that. Or you can have a chest band like this one, and that also one other way of measuring breathing. That would be uncomfortable, particularly if you have to wear it all the time. Now, if you want to add on top of that measuring your heart rate, then you can do with a wristband if you don't care about accuracy. But if you really want accurate heart rate, then you need a pulse oximeter like this one. And I mean, if one of us or some of us feel comfortable with wearables all the time, even when we are sleeping, at least there is some part of our population, the elderly and the kids, who just are so uncomfortable with wearables. The elderly forget to charge them, forget to wear them, and the kids would just take them off and throw them away. So what we were envisioning is that can we take these wearables and let them dissolve into the environment so that the environment can monitor our vital signs and we don't have to worry about charging and wearing devices. But that begs the question, how can the environment monitor your breathing and heart rate? How can I have a sensor here that would monitor your breathing and heart rate while you are sitting over there without any contact with your body? So this is exactly what we did. So the rest of this talk is about a technology that does exactly that. It's called Vital Radio. It monitors your breathing and your heart rate from distance, and it has an accuracy that is comparable with FDA-approved devices that you have to wear on your body. And you can use one device to monitor the vital sign of multiple people in the home. And because we know wireless traverses walls, you can actually use one device to monitor people across rooms in your body. So how does it work? And I'm going to talk, of course, at a very high level about the technology. So, of course, we're going to use wireless. What else? So, here's the high-level idea. Say that you have your wireless device. Your wireless device is going to emit a signal. The signal reflects, we know, of all the objects in the environment, including our body. And we're going to analyze the reflection that arrives at this wireless device to discover the distance, to measure distance. Right? So why distance? How does distance reflect breathing and heart rate? Now, when you think about breathing, it's probably more obvious because when we breathe, our chest expands and contracts. And if we can measure accurately small variation in the distance, then we can get the breathing and the heart rate of the person. Now, heart rate is probably, I'm not sure, some of the audience probably would know and some wouldn't, but actually what happens when the blood is ejected from your heart, that exercises a power on the rest of your body. And as a result of this power, actually your head jitters a bit with your heart rate, and your limbs also jitter a bit with your heart rate, even the skin. So if we can get that sub-millimeter jitters in with the wireless signal, we can capture it, then we can also get the heart rate. So, but how do we capture such variations with wireless signals? Now, again, at the first level, I'm going to go back and investigate this idea in more details, but at the first level, really we can use the phase. So we know that the phase of the wireless signal is a function of distance divided by the wavelength. So variation in the phase reflects variation in distances of the reflector. So we can measure that variation of the phase, infer the variation in the distance, and from the variation of the distance, infer variation in your chest movement, and also infer your heart. Right? So again, this is the first simplistic model. I'm gonna get back to, like, there are multiple caveats with this, but at a high level, that's reasonable. Okay, so here's a person, and we are using the phase to measure his breathing and heart rate. The antenna is, in this case, I think it was about 4 meters away from the person. Let me play the video. Okay, and you can see actually his breathing. These are nothing but his inhale and exhale motion. And at some point, we actually asked him, hold your breath, and you can see. So he started holding his breath, and he will hold his breath for 30 seconds. And you can see that he's not, the signal levels off because he exhaled and he's not inhaling again. Don't worry about him, he survived this experiment. And now he's breathing normally again. So to make it easier for you guys to see the chest motion, I'm going to play the same video at 5x speed up. So notice his chest movement here and how it is aligned with the signal. So this is the phase of the signal with some additional things that I'm going to talk about later. But now let me zoom in on this phase of the signal as a function of time. Okay, so on the x-axis is time, on the y-axis is the phase of the signal. You see the inhales, you see the exhales, and in fact you see these like blips on the signal. And this is actually is not noise. If you zoom in on this, you get nothing but the heartbeats. So you can even like look at them and count them one by one. Now, of course, I showed you one person in the environment and not moving. So let's start talking about each one of these difficulties one by one. So what if the person moves? And what if he moves his limbs, his hands, his legs? So let's see an example of that. So in this example, he was breathing at the beginning of time, and before the 1 minute mark, he moved his arm, and now you see this big motion here. Of course, the arm motion is bigger, but more interestingly, it's kind of like random motion. So what we have to do, if we want really to get the breathing and heart rate, we have to automatically detect periods when the body is taking larger motions and eliminate these periods from our measurements, otherwise we'll get completely wrong measurements. Okay, so how do we do this? Now, again, at a high level, what we notice, which is the other thing, is that this is a periodic signal. This is a periodic signal. So we look for periods of time when the signal, windows of time when the signal is periodic. We eliminate periods of time when the signal is not periodic. And then we zoom in on the rest of the signal. Of course, we have to do a lot of frequency analysis to clean up the signal. And from that, we can get the breathing and the heart rate. Now, again, this assumes there is one person in the environment. What happens when there are multiple people? And I don't have to tell you guys that there are signals, all the reflections from all the bodies are going to collide together. And so here, if you have both Bob and Alice in the environment, the signal reflected on Bob's body is going to collide with the signal reflected on Alice's body as the receiver. And you are not going to be able to separate them just by looking at the face. In fact, not only this, I mean, we know that reflections happen from not just our body, from everything in the environment. So you have reflections from the table, the chairs, the walls, the ceilings. And the face, really, as a receiver, is just a mess. So we cannot really apply that simple analysis that I talked about at the beginning unless we have a mechanism that would allow us to disentangle the signal reflected from different bodies and operate on each one of these bodies separately, each one of the reflectors separately. So how can we do this? So in wireless networking, and particularly in my group, in the last few years, we were studying a problem that's now widely studied in wireless networks, which is localization with wireless signals. So you can take your Wi-Fi device and your cell phone, or the Wi-Fi from your cell phone, and localize where you are in the environment. So of course here the problem is not localization, but you can actually use the localization mechanism as a filter on the signal to filter the received signals into buckets, and then you can zoom in on each one of these buckets and analyze it separately for heart rates. Now, there are many mechanisms to localize the signal that is coming from different reflectors, and we use our specific mechanism, but if you want an example, just think of, for example, wideband and using wideband signals to get ranging. Okay, so let's put it together. Fairly simple. First step, transmit the signal, gets its reflection from the environment. The second step, use some positioning system as a filter on the signal so that you can separate and isolate reflections from different positions in the environment. And the third step, zoom in on these reflections separately and analyze them to extract the breathing and heart rate. Now, of course, there's like tweaks on the algorithms and to eliminate the noise and clean the signals, but let me show you some of these results. So I want to show you a video that has two people, so that to show you that we can deal with multiple people, and I want to show you that the sensor is actually not even in the same room, so it is through walls monitoring of breathing and heart rate. So here's the device is behind the wall. See, okay, the video is playing. So there's one guy here in the environment. You can see that we are monitoring his breathing. The heart rate actually is there, just because of the resolution, you cannot see it. And once the other person enters and sits, the device detects him automatically and start emitting his breathing and heart rate. Okay. So these videos are from an implementation that we built. We built actually the device, including building the positioning system. And the power we use in our implementation chirps. So we use a wideband signal. The power that we have is 10,000 times less than Wi-Fi. It's very low power. That is that agrees with the FCC regulations for that band. We used here in this particular result that I'm going to show you one transmit and one receive antenna. And we did all the analysis in software. So these are the antennas that are fairly small. And here's our setup. These are the antennas for the vital radio. And of course, you have to get the ground truth somehow. And for that, we use a Philips device called LSPDX. And it is an FDA-approved device for measuring breathing and heart rate. But of course, it's a device. It's a device that you have to wear on your body. So you have to wear a this device here for the breathing, and there's a pulse oximeter for your heart rate. And we did 200 experiments with different subjects, male, female, old, young, and different build and sizes. And we in total collected 1 million measurements. So I want to show you some of the results that we have. In particular, one of the issues that we were trying to look at is if you are monitoring the person, then you want to be able to monitor independent of whether the person is facing the device or has their back to the device or the side to the device. Because like when you visualize it, I mean, you think about the chest has to be facing the device. But actually that turned out to be completely not true. So we run these experiments with the device 4 meters away from the person and different orientation for the person. Let me show you the accuracy in comparison to the FDA approved monitor. So here's the breathing. And as you can see, it's pretty high accuracy. It's between 97 to 99. This is much better accuracy than like many of the chest bands that you have. And here's the heart rate. And again, very high accuracy, again, around 97, 99% accuracy. And you have nothing on your body. Okay, so then let me show you results from multiple users. So we had multiple users in the environment. Some users are closer, 2 meters, 4 meters, 6 meters from the device. And again, I'm going to plot for you the accuracy as a function of the user distance with respect to the device. And here's the breathing rate. And again, you can see quite accurate. There's the heart rate. So really the accuracy does not change that much with distance. What's changing is the variance, like this small, the variance becomes slightly larger as the person is further away. So in the previous videos I showed you, you can see clearly that it's tracking in real time the breathing. But I want to show you also that it tracks in real time the heart rate. So what we did in this experiment, we asked the subject to exercise for a few minutes and then sit on the chair, and then we started monitoring them. And I'm going to show you here the heart rate as a function of time, both for the reference, the FDA approved reference, and for our device vital radio. And as you can see, it tracks your heart rate. So we believe that this technology can enable our environment to become smarter and to follow our vital signs and use that information hopefully to improve our health and to have ubiquitous health monitoring. Now, of course, there are some limitations, and I want to tell you about the limitation of the current implementation of vital radio. So one of the things that we have in the implementation that the results were collected with is that the distance between different users had to be about 1 to 2 meters. Because if they were too close to each other, then the device thought of them as just one person there. They started making into each other. And the other thing is that because we are using ultra-wideband, the distance is limited by the power that's allowed by the FCC, so we can monitor you up to 8 meters away from the device. And finally, we detect periods when the person is quasi-static, like typing on a device or watching TV, and we extract the measurement from those periods of quasi-static, but if you are walking, we cannot simultaneously get your heart rate and breathing. We can just detect it and eliminate those periods. So I want to show you other video, which is actually, it's baby monitor. So it's going to resonate with the parents in the audience. So parents are always worried about their baby breathing. This is actually a video. So you see time passing, this is the night vision, and the baby is sleeping, so you don't really see anything happening. And my friend always pokes her child to make sure that he's still breathing. So what we did, we augmented this with the breathing from vital radio. Yeah. I don't have kids to
No,
poke
I
them.
just mentioned the poking with the breathing. Sorry.
Okay, so this is the heart rate of the baby. This is his breathing. In fact, like baby's heart rate are significantly higher than adults, and this is very good heart rate for his age. So before finishing, I want to tell you where actually we, like, as I said, I mean, this has started really from when we started, we were looking at localization problem. We weren't looking at being able to detect vital signs. Because, like, well, not doctors, that was the last thing on our horizon. And we came to it from, okay, can we actually localize people very accurately just using reflections without asking them to wear or carry anything on their body? And when we discovered that we can do this, we actually started asking, okay, so can we get higher accuracy to the point that we can start tracking actually their heart rate and their breathing and vital signs? So I want to show you the video of tracking motion. So we all know about like localizing people using wireless, like Wi-Fi and LTE from their devices, but here assume the person doesn't have any device on themselves. The device actually is the transmitter and the receiver are both one sensor. They are in different rooms altogether. And the device is just monitoring the motion of this person purely based on the reflection of his body. And of course, the reflection of the environment are confusing to other things, but we can eliminate them. So here, this screen is the screen of the device, and this red dot is where the device thinks the person is currently. So let me play this for you. So notice how the red dot is tracking him. Of course, the spiral is just for visual clues so that you can connect with the physical environment. You can see it's tracking him pretty accurately. And this guy doesn't have cell phone, Wi-Fi, nothing on himself. And not only it can track your whole body motion and localize it, you can track actually body parts motion, so you can use it to interact with devices in the environment. You can like activate the lamp or turn it off by just pointing at it. And you turn off the screen by pointing at it. And say, for example, you forgot to turn off the light in some room, you left the room, you don't have to go back. All that you have to do is just point at it from the other room, wherever you are, and the device will point out. So if we go back to where we started, so we started with 5G, and of course, this is not about communication, but really this is about what is the next hub for the home. Like, okay, so like it's Wi-Fi, is it a new device, is it a new radio? Maybe it's a radio that has all of that, and maybe it's a radio that allows new interfaces with the environment. Okay, so we all talk about IoT and the Internet of Things and controlling the lights and controlling the shit. But imagine a device in your home that can detect when you go to bed, get when you wake up and start sitting in bed so that it opens the shades and takes what you do when you wake up. So okay, if you spend 20 minutes in the shower, it knows that after that you go to your kitchen and start making coffee. So start the coffee maker before you finish your shower. And you can start interacting with the environment by presence, as opposed to today, if you want to, even with the most advanced, let's say Hue, Philips, the Hue lights, you have to use your cell phone to actually activate, deactivate. This is not the easiest interface. The interface is your presence and your judgment, and even your emotional state and health state extracted from your vital sign. So maybe 5G can offer something beyond even all of the advancement in communication and throughput, and something also that has to do with the interface with the environment. Thanks. So for the breathing and heart rate, 8 meters. For the localization, it goes up to 10 to 15 meters depending on the environment.
So what I'm wondering about is anything like this can be used to find people. I'm thinking search and rescue.
Yeah.
And so the distance might be.
So, I mean, really the distance is limited by the power, which is a limitation of the FCC. So for rescue missions or for, like, depending on the entities in the government who are going to use it clients that will have different rules that they have to abide by in terms of the power limitations. So maybe for rescue missions, the FCC will allow higher power.
If a person there, they don't care about heart rate, they care about breathing.
Yes, yeah. As long as he's breathing, I guess it's the same stuff.
Well, they're not breathing, it doesn't matter, right?
So you're using Wi-Fi frequencies for this, correct?
So,
Or different frequency,
no,
and I'm
we-
wondering about interference, actually.
Yeah, so we are using ultra-wideband, as I said, technology. It's in the same range as 82.11a, so but it's wider band. It's below the noise level. Just simply FCC would not allow it if it's above
It's like
the
radar.
noise level. Yeah, it's you can think of it as a personal radar at very low power because radar actually
No,
has
no,
very
right.
high power. Yeah, so it doesn't interfere with Wi-Fi. I mean, we run it in the lab with all Wi-Fi.
And the existing signals don't interfere
And
with
they
it,
don't interfere
right?
with each other because they kind of like, at some level, they have some of the radar technology that they are hopping away from each other.
You mentioned like you're limited to like this quasi-static case. So I was wondering like if there's a challenge of associating a given signal with a given person, right? You might see like two signals, you can separate them, but you need to associate them and like suppose these guys swap positions.
Okay, so actually when people cross and all of that stuff is not a problem. But the only thing that you can ask, okay, so I see these two dots moving, like which one is Dina, which one is Muriel? And this is unpublished work yet, but we can classify based on wireless signal among a small number of people, between like 10 people. So the people in the home, we can identify who is who among these dots.
And so I've seen in spy movies that the FBI does with acoustic signals when they want to identify people in a big crowd. Can you do it acoustically also, in addition to Wi-Fi? Like, yeah, the FBI.
Our algorithms are in software. I mean, in terms of the acoustic, you have to think about whether the signal actually will be able to, just like how it gets attenuated with obstacles. And the other thing is the relation. I mean, of course, acoustic is transferred as a different rate. It's not the speed of light is different. So the relation between the frequency and the speed at which the signal is transferred, in addition to what kind of reflection it has on the different bodies, because we know that signals interact differently with different reflective material.
So I think there was two more questions, 1 and 2.
I was curious in terms of making some of the stuff that you were talking about a reality. How much of it do you think is solving technical problems, and how much of it is more of the design, kind of finding the right, kind of the creative part of finding the right environment, finding the right sort of the right place to put the device that really so it works seamlessly.
So I think the technological things, I mean, when we started, I mean, this is, at the beginning we didn't even know whether we can get the signal at all. And then the first device was able just to detect the presence, and then we could localize it, and we could localize more accurately. So I think technology is always advanced, and advanced very fast. There are the other issues that when we started, for example, we didn't know what the application would be. We were just like, oh, it's cool, I can localize it without having you to. But then if you think about it, it has so many applications. So in gaming, now you have to stand in front of your gaming console. You cannot interact with the physical. Let's say that I want to hide, like dodge a bullet by hiding behind this podium. The gaming console just stops being able to track. So you can add it to augmented reality so that you can start interacting with the environment while the system can still track you. Rescue missions, I mean, we talked about that. Elderly monitoring, I mean, elderly falling and elderly mobility and aging in home, all of these like big issues with the healthcare industry, and we can use these devices for. So I think it's really realizing the application and which one of the application is more ready to adapt the technology. Of course, there are security, privacy issues, and I mean, we can talk about them for the whole day, but that's probably not the wisest use of time.
Online and then
I hope you just didn't answer my question about the privacy. Whether your neighbor should see you or not, whether you watch it.
It depends on, I told you, it's all about the application. So the application is to see your neighbor. So I
Armand is interested in that.
yeah, I don't know. All about your interest.
Is there a way, for example, to have a device that, for example, protects you also at the same time? For example, at the same time we have jamming, could we also stop other people from locating us or knowing things like
You can get a bunch of dummies like.
Your dog.
The way we deploy the technology is with directional antenna toward the inside and choosing the device to track your neighbor. Now, of course, you can take that device and flip it and try to track your neighbor. So there are multiple ways that the neighbor can use it if he suspects that you are actually tracking him.
that? Thank you.
Okay, good. Thank you.